Our group took on the task of assembling and modifying the original gamma Stirling engine design to improve thermal efficiency and power output. Our 3 ideas for design modifications were adding a chimney, a regenerator, and cooling fins. The chimney was designed to increase heat transfer to the heating cylinder, thus increasing the temperature differential. The purpose of the regenerator is to recover the thermal energy input from the heating process during the cooling process. Finally, the cooling fins also serve to increase the temperature differential by increasing the rate of heat dissipation in the cool cylinder with a large surface area. The Stirling engine is an example of a thermodynamic cycle consisting of 4 processes: constant temperature expansion, constant volume cooling, constant temperature compression, and constant volume heating. Our project focuses on the gamma Stirling engine. As seen in the diagram above, the gamma Stirling engine functions most similarly to the beta Stirling engine. The only difference is that the gamma Stirling engine contains a separate cylinder for the power piston.
For our calculations, we began with the assumption that our Stirling engine would operate as a closed system. Assumption 1. This allows us to model the network as the sum of the expansion and compression works. Then, by using assumption 2 that the air in the system would act as an ideal gas, we were able to use the ideal gas equation to simplify to equation 2 and 3. When simplified, our network equation took the following form. Here, one can see that improvements to our engine would be increased the most by improving the temperature differential as well as the compression ratio. Equation 5 shows the basic efficiency equation for a Stirling cycle. However, our machined regenerator allowed us to simplify to equation 6 using our 3rd assumption that says that the energy used in the isometric heating portion of the process can be entirely recovered during the isometric cooling portion. Using these equations, one can see the direct effects the chimney and regenerator would have on our system. The chimney would increase the temperature differential by creating a stack effect that would draw oxygen up and through the chimney, increasing the size of the flame and the heat output, while also preventing the hot air from reaching the cold part of the cylinder. The regenerator would act to increase the thermal efficiency and let us approach the limiting Carnot efficiency, as one can see on the right side of the screen. The first model one can see here is a SolidWorks rendering of our chimney, which slides over half of the heat exchange cylinder, as well as the fuel source below. Notice that the diameter of the chimney is large enough to extend beyond the fuel source, allowing air to flow in and up the chimney. This next model shows a SolidWorks rendering of our regenerator, which is connected from the hot end to the cold end of the heat exchange cylinder. While not explicitly shown in the model, we filled our regenerator with steel wool to provide insulation in recycling the waste heat each cycle.
In order to test the effects of our modifications, we used the rotary motion sensor to measure the rotations per minute of the flywheel, reflecting both the changes in power output and efficiency. We ran each model of the engine at least 3 times, recorded the maximum RPM value once it reached a steady state, and calculated that average value. The chimney was made out of a thick aluminum pipe with holes cut out to slip over the fuel tank and heat cylinder, and with a slanted end for the heated air to escape, directed away from the colder side. The regenerator was made out of a 1/4-inch copper tube, bent to connect each end of the heat cylinder and filled with steel wool. We drilled holes on the cylinder slightly smaller than the diameter of the tube and attached the copper tube using a high-temperature epoxy. As you can see here, both the regenerator and chimney had significantly lower RPM values than the benchmark, which was the opposite of what we were expecting. In our air analysis, we found that since the chimney was made out of a thick aluminum, which was highly conductive, but also sitting on the heat exchange cylinder, we found that it actually conducted the heat out of the hot side of the heat cylinder, therefore removing it from the system. And this actually decreased the temperature difference between the hot and cold side, which slowed down the engine and decreased the power output. For the regenerator, the main problem seemed to be that the epoxy we used to attach it melted during testing. This compromised the connection between the two, and we were not able to obtain accurate test results. Additionally, the walls of the copper tubing that were available were very thick, so airflow was restricted more than we anticipated. Since our original 2 modification ideas didn't work out well, we went with a much simpler approach, and we tried taking an aluminum soup can and cutting holes in the bottom to slide over the fuel source and the hot side of the heat exchange cylinder. This was to serve 2 purposes. It was to decrease the amount of heat lost to the environment by providing insulation and trapping heat within the system, and it blocked the hot air from the cold side of the heat exchange cylinder. Similar to the intended effect of the chimney, this increased the temperature differential and increased the maximum efficiency. As we can see here, the aluminum can insulation modification was much more successful than the modifications in the first round of testing. With more time and resources moving forward, we would like to fabricate these modifications using better materials and manufacturing methods. We actually attempted cooling fins made out of aluminum tape and misted them with cooled water, but that didn't work out well, and that was an alternative for the fins that didn't fit from the machine shop. So moving forward, we would make similar fins to those that we were given, but align them better, and the can would be replaced with a custom fit housing made with better insulating materials. We believe that with these components, the power output of the engine would increase significantly. We would also like to be able to test the effectiveness of the regenerator when properly installed. To do this, we would look further into the optimal materials to make the regenerative, the ideal size and shape, and the best method to attach it to the heat cylinder. With the materials we have, we would work with the machine shop staff to create a stronger connection between the copper tubing and the cylinder via soldering or brazing. Finally, we would also look at materials and lubricant to decrease the parasitic torque in the original design from the friction between the piston and cylinder as well as the flywheel to further increase the power output and efficiency of our design.